When we're solving an ODE, we're solving for a function. For example, if you have the dy dx in the equation, then we're solving for y, but y is not a number, y is a function. So we'll see some techniques on how to do that later, but for now we're trying to study the ODE by sketching the solution, how the solution looks like without even knowing what the solution is, without knowing or having a formula for the solution. One of the techniques is called Isoclines, and the idea is actually quite simple. You remember that a derivative is a slope, right? So if we can find the derivatives, then we can know where the slope is of the function, and then we can draw the function according to the directions of those little arrows from the derivative. And one of the techniques that is called isoclines, the idea is to set the derivative to be equal to a constant. Now, why do we want to do that? So if you look at an ODE like this one, which you have the dy dx isolated in one side, and on the other side you have a bunch of things, an expression that has x and y, then we can set the derivative equal to something, to a constant. This way, the derivative, the new equation will not have the derivative anymore. So you have a constant equals to an expression, and then we can solve for that expression. We can solve for x and y. Now the numbers, right? We can plug some numbers and see what the solution is. And in any of those solutions, then we know what the slope is, because the slope is a constant. So here's the idea. So let's say, for example, we have an ODE that it's like this. So dy dx equals to negative x over y. We don't know what y is, right? Y is a function. So we can set, so let's set the derivative to be equal to a constant. Now, is the derivative a constant in this ODE? No, it's not, well, not necessarily, but we are setting equal to a constant to see what happens. So we're kind of sort of like a trial and error to see what's going to happen. So for example, if I set this, if this constant is 0, let's see what happens if the constant is 0. So here, case number 1, let's set the derivative equal to 0. Okay. So in that case, if we take the ODE, then this means that 0 is equal to negative x over y. See, now we don't have the derivative anymore. We have a simple equation, and we can study this equation and see how it looks like. One thing you can observe is that in order for this to be 0, then x has to be 0. And also, one condition here is that it's being divided by y. So we are assuming that y has to be different than 0, because if y is 0, then we have a problem. So notice that we found something here. We found a conclusion. If we set the derivative equals to 0, then we have this conclusion here. What does this mean? Well, let's graph it. So if we draw that solution and see what happens on the plane here, let's take a look. So if this is the y-axis, this is the x-axis. So x equals 0, that would be right here in the middle, right? And y is different than 0. So that means that along these points here, right, all these points, it's where x equals 0, right? Right over here, x equals 0. Right over here, x is also 0. Here, x equals 0. But what is happening here? What is happening here is that the derivative is 0, because that's what we set to be equal to. That means along in all those points, then we can draw the little arrows. The little arrows will be horizontal because derivative equals 0 means that the arrows, right, the slopes are 0. So the tangent lines are all horizontal like this. Here, there's nothing going on here because remember, y has to be different than 0. But everywhere else here along x equals 0, the slopes, they will look like this. So we can keep this information. And then what we're going to do is to get new cases, right? I don't want to say case number 1 because we can have many. But let's say here another example, another case. Let's set the derivative to be equals 1. So what's going to happen if the derivative is equal to 1? Let me move this over here. If the derivative equals to 1, then we go to the ODE up there, here, and then we see that this will become 1 equals negative x over y, right? So we're setting this equal to 1. Again, is the derivative 1 the solution in the ODE? Not necessarily. We're setting it equal to 1 to see what happens. So this means that now I have, if I multiply y here, this gives me y equals negative x. Again, y has to be different than 0 because y is here in the denominator. All right. So what do we do with this information? What is y equals negative x? Y equals negative x would be this line here. I should put the points like this. Right? So remember that this line here is where y equals negative x. What is happening along this line? So these are all the points. Here it's open. What is happening at these points which satisfy this information here? What is happening there is that the derivative of y is with respect to x is 1. That means the slopes there, they have tangent equals 1, which is 45 degrees, right, going this way. So here I can draw the little slopes. They will be like this, 45 degrees here, 45 degrees, 45 degrees, right? So I can draw all of these points, at these points, the arrows going 45 degrees like that. Okay. Let's do 2 more here. Let's see another case. Let's set the derivative to be equal to negative 1. Notice that I'm choosing these constants, right? Remember that I'm setting the derivative equals to a constant. I'm picking easy constants, right? 0, 1, negative 1, because I know how the derivative looks like. So if the derivative equals to negative 1, then this would be negative 1 equals to negative x over y. Again, that's according to the ODE here. Okay. Well, this means that the negative y equals negative x, which means y equals x. Now, what do we do with this information? And again, y has to be different than 0. What do we do with this information? This is a line that goes like this. Right? It's a straight line going through here. And what happens at these points? Well, at these points, the derivative is negative 1. Derivative negative 1 means the line is going downward like this, a 45-degree angle right down. So I can draw the little arrows like this, pointing 45 degrees that way. Why is that? Because the derivative is negative 1 at those points. And I can keep doing this. Let's say, for example, that what if the derivative, if I set the derivative equals to 2, let's say, what happens? Here's another case. Set the derivative equals to 2. Well, this means that 2 is equal to negative 2 over y, and this will give me 2y equals negative x. That means y is 1/2 x. All right, again, y is different than 0. What do we do with this information? Well, negative 1x is also a line that it goes down, but it's not as inclined as this one here. So the slope is negative 1/2, so it's a little bit less inclined. So that means that would be this line here. So the angle is less inclined. So what is happening at those points? Well, at those points, the derivative is 2. The derivatives 2 means that the slopes are very inclined upward, right? Positive 2. The derivative is positive 2. So it's very inclined. So that means they're like this, almost not necessarily, not vertical, but very inclined like that. They're not vertical. They're greater than 45 degrees, right? Maybe 70 degrees, 75 degrees or something. Okay. So I can keep doing this. I can keep setting the derivative is equal to a constant, to several constants, and then plot the points and then draw the little arrows according to that. So I think we have enough information to kind of discover what the solution looks like. So now I'm going to look at this graph here, right? Look at this graph. Now I see a directional field, right? The little currents, if I drop a little boat there and see what happens to the boat, the current will push the boat according to, we'll describe a trajectory. So for example, if I drop the boat right over here, then this boat is going to move this way. Right? We'll keep moving. Obviously, there will be some currents here that we didn't draw, but according to these arrows, it looks like it will push the boat this way. Eventually, we'll go here. It's pushing now horizontally, and it will keep pushing, pushing, and then it will go down, right? And it will keep pushing, pushing, and then at y equals 0, there's something that happens here. We don't know what it is, right? So we don't know what happens there. But notice that I'm describing a trajectory now. It seems like it's a circle, right? In fact, the solution is a circle. If you had dropped the little boat right over here, then this boat would have gone this way. So that's one solution. If you drop the boat someplace else, you're gonna get another solution from the same family, right? If you drop it right here, then you will see something like this. Right? So something like that. If you drop it here, obviously you will see something like this. Right? So that means this is the graph of y, our original y, okay, from the ODE. And that describes the solution of that ODE, which it is a circle.